Hello.
Hello, Eric.
Like we are at the moment 17 people in the meeting, whereas on LinkedIn we have 31 attendees. So I think it's fair to give it a few minutes maybe before heading off.
So, Eric, I'm recording the session.
Very good. Thank you.
So, welcome. There's a question in the chat whether the recording link can be shared after the event.
That should be fine, I guess. Eric, should we start?
Yes, there was invite on Google Meet that had snuck into the calendar invite for some people, so I had to go over there and get them invited. So give it 30 more seconds so they have a chance to get the intro, and we'll join.
Good you find out, otherwise you would not know about this.
Yeah. Multiple video technologies everywhere. So. So 23, yeah, I think we might as well kick off. Good morning, everyone, and thank you so much for joining us for today's SUREWAVE lunch seminar on floating solar and wave breaker technology for offshore environments. And I'm sure that since you are here, you're just as excited as us to have this lineup of experts in the field to present the material to you and also be available for the Q&A after the meeting. I'm sure many of you have lots of interesting questions. So to kick this off, we will go through some key findings of this project. First of all, we will hear from Balram Panjabi from SINTEF, who will provide an overview of the SUREWAVE project and offshore floating solar technologies and wave breakers. Then I, Erik Larsen from Sunlit Sea, will discuss the challenges of offshore floating solar generally and how innovative solutions like the one we have worked with in this project can help address them. And finally, which this will also be the longest part of the presentation, Thomas Felke from Clement will present the development of floating wave breakers and their role in enhancing system stability for offshore floating solar. And yeah, we are thrilled to have you here with us and look forward to your questions during the Q&A. So let's get started. Balram?
Yes. Yeah, thank you very much, Eric, and thanks a lot, all of you, to join this session. Yes, so I am Balram Panjwani, Senior Research Scientist at SINTEF. So I am the official coordinator of this SUREWAVE project. SUREWAVE project is funded by European Union, and which started 2 years ago and is going to end in September 2025. So basically, the SUREWAVE stands for the Structural Reliable Offshore Floating PV Solution Integrating Circular Concrete Floating Breakwater. Do you see my slide, by the way? Just
Yes.
Yes.
Thanks. Yeah. So, what are the main key challenges when we are moving from the landlocked FPV to the offshore FPV? So normally you see when it comes to the landlocked, first thing is there is no current profiles, and the wind profiles are also mild, and the waves are also mild. But when you move from the landlocked onshore to offshore, deep offshore, normally you get current profiles, you get the high wind speed, and then the extreme wave events, which basically has quite few challenges. Like some of things like extreme, you have the extreme environmental events, you have the constant fatigue on the joints and connection, you have the salt water corrosion and UV degradation, biofouling, and this constant movement of this FPV modules and the breakwater could result in micro cracking and de-alignment. And one of the challenge that since these technologies are at low TRL, normally they are not well established design standards, guidelines, and legal regulations. So that's why in order to address some of these key challenges that is addressed by the SUREWAVE project, we would like to design an FPV system that can withstand the wind of 25 meter per second, wave of 14 meter, and current of 1.2 meter per second. And then since today you see there's a lot of focus on sustainable material. So our goal is also to bring new material which are more or less close to the 100% circular. And that is one of the key goal as a part of the SUREWAVE project. And then we, at the same time, we want to have improved service life. And then since we are developing a new concept, we would like to perform some of the assessment, for example, to check these CO2 footprints, how this system affects the marine life, and how we can reduce the levelized cost of energy production. Considering, levelized cost of energy. So considering this one, the main objective of the SUREWAVE project is to basically develop and test an innovative concept of a floating FPV system consisting of an external floating breakwater, which is made of new circular material, which will act against the severe wave wind loads on the FPV structure itself, which will allow increased operational availability and energy output. So this is the main overall idea of this project. So mainly you see in this one, we came with the idea of having a floating breakwater in front of the FPV. The main goal of this breakwater is to protect against the severe, mainly the short waves, which are critical to the internal FPV. So this breakwater will protect this internal FPV. The more details, calculations, and simulations will be performed by Thomas in his presentation. And the goal is not to basically, you see the entire system when it comes to the long period waves, normally the entire system will float, but the breakwater will attenuate or mostly remove some of these critical waves which are dangerous to the FPV. Just to show this concept, we have made one video which would like to show here. This was a short video of the SUREWAVE overall concept, but within this one, we have multiple key research pillars. So first research pillar is basically to come with the innovative breakwater concept. And then second is to introduce sustainable material into this breakwater. And since these systems are designed into the very complex environment, so we would like to bring some intelligent predictive modeling tool. And they are mainly in this project, we are 7 partners from the industry and research, which are mainly coming from 4 European countries. So as you can see, this map shows the partners representation. And when it comes to the design, like which environmental condition we should take into consideration. So the locations in this case we have chosen, which include both mild and harsh environmental, mainly considering the different wave directionalities and location, with the wind, which should be higher than 25 meter per second, current 1.2, and the wave height of 14 meter. So what we have found, actually we found 3 different locations, starting with the Baltic Sea, which is a mild condition. And these are some of the wave parameters here. And wave and wind parameters. We have the Western Mediterranean, which is again a mild, but a different wave and wind parameters. And then we have taken a one extreme or harsh condition, which we have taken in the greater North Sea region. So once we have identified the location, then we start looking into what are the key objectives of this SUREWAVE project. So first one is the novel floating PV design for offshore extreme condition. So in this case, we would like to work on this novel breakwater concept, which will help to protect and attenuate the wind, waves, and current, which are harmful to the internal FPV elements. We'll see that in this one, we would like to develop a coupling between the breakwater and the internal FPV, which will also include the innovative mechanical joint design. And another aspect in this one to look into this anchoring and mooring of the complete system. And the most important aspect was to how to do the layout optimization, like whether we should take the circular, rectangular. There are multiple parameters to be considered. And when it comes to the internal FPV, in this case, we have chosen concept from Sunlight Sea, although the concept proposed by SUREWAVE is generic and could be applied to any landlocked FPV system. But there are few reasons why we chose this concept. One is basically the concept is built on marine grade aluminum, which is like more or less 100% circular material, is easy to install and deploy, and it has a reduced cost. And when it comes to the breakwater, we have been considering the various parameters when it comes to the designing, like we'll look into the width, length, height, shape, with or without keel, under various sea state. And this is some of the schematic where you can see the wave comes, which will there is a breakwater, which will protect this internal PV to this waves condition. And the more discussion will be presented by Thomas in the next presentation. And in under this objective 1, we are basically analyzing a different layout, like starting from the circular polygon, triangle, and oval shape. And in this case, we have made a very complex matrix. Like we have this, you can see on the one axis, we have different shapes, and on other axis, we have various parameters. So basically, we'll have created a matrix giving the plus and minus on the each parameters, and we see which design or which layout is the most optimum. So the detailed result will be presented by Thomas. Yes, so once we have designed the breakwater, the second objective was to basically introduce the sustainable materials in this breakwater. So as you see today, most of this breakwater, they use the traditional concrete, and this traditional concrete consists of large amount of cement, which is one of the CO2 emitter actually. So our goal is to basically come with a new circular concrete, mainly this structural element, which include the high performance concrete and lightweight aggregate concrete based on the circular material. And as also you can notice that today most of these breakwaters are designed using the EPS, which is some form of plastic, which is not good for the marine life. So as a part of the SUREWAVE, we are introducing a new cellular material, which is made on the circular composition in order to reduce the CO2 as well as to have less impact on the marine life, because we are not using plastic in this concept. And at the end, we would like to do some material durability assessment through corrosion and biofouling testing and resistance. And with this one, we are proposing a lightweight solution with the reduced production and installation cost, and that should be very easy to cost and transport. So in this case, we have done a multiple solution, like with respect to choice of material, like taking a different recyclable glass, lightweight aggregate, recycled concrete aggregate, slags, fly ash, and other waste streams. So we are basically taking a different raw materials. And then we are also measuring, since it's a new material, so we'd like to see whether it fits to the offshore condition or not. So we'll do a lot of measurement with respect to the compressive strength, density, mechanical, physical, and other durability property assessment. And that is also done as a part of this SUREWAVE project. You can see we have different samples, and each sample we are making, and then we are sending to the lab to do all this assessment. So since this project, we have quite many, connections and systems. So we would like to come with a new predictive computational modeling and simulation framework, which will be combining, like we have this improved, for example, first one, we have this couple arrow hydrodynamic modeling tool, which basically will be utilized to understand the motion and loading prediction of the complete FPV system. Second, we are developing this machine learning based material property modeling tool for basically finding the optimum concrete material composition. And at the end, we are also bringing this structural integrity modeling tool, which basically will be used to assess the remaining lifetime of the component or other materials properties or structural properties. Yes, so when it comes to this materials modeling tool, it's a very kind of innovative concept. In this case, we are building a large set of database considering the various composition of this concrete mixture. Like normally you see the concrete consists of cement, fine aggregates, coarse aggregates, filling powders. So in this case, we built a database, and then we have the concrete properties. And then using this database, first we'll train the model, and then we use this trained model to predict the material property behavior, and then we will document all our results. Yes, so when it comes to this structural health management system, and it's one of the very complex tools we are developing here. In this case, what you can see, we are doing this aerodynamic and hydrodynamic assessment. And once we have that one, in parallel, we have this materials modeling tool. We have the structure integrity modelings using the finite element technique. And so these are the numerical models using from low fidelity to the high fidelity. So we'll be producing a lot of data set from there. And then we have the monitoring system, like we have the corrosion sensor, we have this force sensors. So we will taking the database from there. And by combining all these numerical models, data from the experiments, we are building this structural health management system. And the goal basically is to estimate the remaining fatigue lifetime to be used in the maintenance, inspections, and replacement periods. And you can do all other structural integrity diagnosis. And then, so once we have done this one, now we have gone from the breakwater to the sustainable material to the numerical tools. So since we are developing a different kind of elements here, so our goal basically is to assess the different component using the lab facility. So as you see, this complete FPV system consists of very complex connections. And based on our study, we found that there are few connections. They are one of the weakest in the entire system. So in this case, we'll be doing some structural assessment like the connection between the breakwaters, between the brake motors and solar modules, and connection between the solar module to solar module. And in addition to that, we are also doing some busing test, mainly the using at Marine Advanced Facility at 1/10th scale. And then at the end, we also do the long-term behavior of this concrete breakwater prototype. So this is the first test, like mainly that you see there's a connection between the PV to PV module, which Centab is assessing using their advanced testing facility. And then we have this connection system between the breakwater to breakwater. And then we have the connection between the breakwater and PV module. So you see this, this assessment we are doing in our labs to find out the fatigue life. And then once we have this concept available, so we are basically analyzing the, as you can see in the picture, we have done our first set of wave tank experiment at using marine facility. So where we have this PV matrix, and then we have the breakwater, and we are basically understanding the behavior under different wave conditions. And normally the first set of database available, and primarily we are using this database to validate our numerical models. And this is the last what we are doing the validation. So in this case, we have built this prototype of the breakwater, and this is made of complete circular material. As you can see, this is the outside is the high performance concrete, and inside the breakwater we have the lightweight aggregate. And this is going to be placed in Spain for roughly in the one of the offshore condition at Acuna facility will be roughly for 10 to 12 months. So now this is coming to my end or last slide of this presentation. So the main key takeaway from the SUREWAVE project. So we are building this floating PV solution, which is mainly to work in the North Sea environment. And then we are building a floating breakwater module, which is made of circular and sustainable material. We'll be making machine learning model to predict the concrete properties. And then we validate this concept like under the lab testing, hydrodynamic assessment, concrete lab testing, concrete prototype. At the end, we will do the techno-economic assessment of the full concept. So this one, I would like to thank you all. Thanks a lot. Yeah.
Thank you, Balram. That was a great introduction. And now it's my time to talk a little bit about the challenges with offshore floating solar. And I will shortly present my screen to you. One moment. See. So can you all see my screen? I don't need confirmation from all maybe, but someone
Yes.
can say yes.
Yes.
Good.
Yes.
So I'm gonna talk about our product a little bit to give a little bit of background and generally the challenges with offshore floating solar. And lastly, I'll touch into how these wave breakers can actually help and what the impact and of that can be for us and our vision going forward with this technology. So the key challenges of offshore floating solar systems, as we see it, is that you have to operate in these harsh environments where these offshore waves are pretty high with strong winds and saltwater corrosion. all things that impact durability and can cause quite severe failure modes, to be honest. And there's high risks regarding operational conditions because the anchoring and mooring must withstand all these dynamic forces that are pretty hard to predict and are really hard to handle. But most of all, they're pretty expensive to handle normally. So we have wave loads and we have biofouling that both affect the system. Now in this system, we'll be not talking so much about biofouling, but it becomes an operational risk because you have to move out to the system to clean it. And there's a high chance that systems deployed offshore can become economically infeasible. We've seen that with floating wind to some extent, and it's crucial that we make this economically feasible, otherwise it won't be usable at all. So energy output and reliability, it can be a little bit difficult in these severe conditions, specifically if you have strings of interconnected solar panels and you have wave-induced mismatch losses, and as I talked about, the fouling that can make it hard to operate. In some conditions, you might even have to consider sheltering or disconnect the system. So our role in the SUREWAVE project is that we have operated these advanced wave breakers. Oh, sorry, I skipped a slide. So about Sunlit Seas solution, what we have is a durable design. We have this aluminum floaters that have a high structural integrity, and we have laminated the solar panels on top of this floater. In case you haven't seen it, I can show you a quick video about how it looks. Let's see. There we go. If you can see my screen there, you can see this is a project we did onshore actually. But what you can see is that these marine grade aluminum floaters, they resist corrosion and impact, and they give an enhanced cooling, which is good because it gives you a higher energy yield. And they're pre-assembled, so it's a modular system that is pretty easy to install. We installed this whole installation in one day, actually, the one you saw. So it's a configurable system also, so you can lay it out in various configurations. For instance, you can have a square configuration, rectangular, it can be round in a manner that Thomas will show you a little bit later. And not the least, it's an eco-friendly approach. Aluminum does not have the same negative impact on environment as microplastics and marine disruption. Also, maybe not that important, but it's visually appealing. I would like to mention that because there's a lot of resistance, especially in Norway, towards floating wind and the visual appearance and the sound it makes. So this system is completely flat and you can barely see it from afar. So the role in the SUREWAVE project for Sunlit Sea is that we've collaborated with Clement and the other partners to develop this wave attenuation structures, which is the wave breakers, of course, but also these mooring systems that connects the wave breakers with the floating solar system. I will see figures of this in Thomas' presentation. And we've been collaborating with the partners to perform testing, and it's still ongoing. So it's both in simulation, in wave tanks, and in offshore environments. And this has given us data from these real conditions have been really useful to improve design and change, for instance, the hinges of our system. Yeah, we've been investigating eco-friendly materials especially for the wave breakers to minimize the environmental footprint. So the impact of this is that the increased resilience can make a system last much longer in these conditions, which is important because it's expensive to install. It can for us as a company, it can give us access to open sea conditions and nearshore conditions, which otherwise would be non-bankable, viewed as non-bankable. And we can get more energy output from the system by keeping the waves in check a little bit. So it's less wave-induced mismatch losses and less maintenance. And last of all, it's a long-term solution that is really scalable, and it's really configurable. Even though we're now considering only offshore conditions in this project, there's a lot of potential for investigating, for instance, wave protection from only one side of the system, or the most critical side regarding the wave loads. So going forward, yeah, we are really looking forward to testing this in real-world project. We have real-world project that this is relevant to test on, and it will be very interesting to see now towards the end of the project how the economic assessment of the whole system will be, because that's a really crucial part for us if we're gonna prioritize these offshore conditions compared to other nearshore or on land conditions. So that's all I wanted to talk about before giving the word over to Thomas, which is gonna take you through the wave breaker design and give you some insights from his work. Thank you. Thomas.
Yep. You see my screen?
Yes.
Okay, perfect. So yeah, I would also like to welcome you to our information event with the status quo on the SUREWAVE project. Today I want to give you more details about the floating breakwater, which is an essential part of the concept. One of the three pillars of the SUREWAVE concept is the research and development of an innovative breakwater for floating solar installations in extreme offshore conditions. The objective is to minimize the impact on functionality in these offshore conditions by providing an external barrier without the need to strengthen the floating PV elements themselves. Furthermore, the system is to be designed to generate electricity for an extended period of time. And the effects and loads on the PV system should be limited, thereby extending its service life and reducing the need for extensive maintenance. However, the primary reason for the external breakwater is that the floating solar system would be unable to withstand the extreme offshore conditions without protection. Especially high frequency waves are a significant risk. What do we actually mean by extreme offshore conditions? For this European project, we have selected 3 locations with different conditions, including mild, moderate, and harsh. These selected sites are shown on the map. They have been assessed using statistical analysis based on hindcast data. This data is shown in the diagram. For simulations and experiments, combinations of wave period to significant wave heights were determined. The ion swap spectrum and the steepness criteria were used because the steepest waves are the most critical for both the breakwater and the PV system, even though these steep waves will most likely not occur. But yeah, these are the maximum values for the selected locations. Here again, the combinations of wave period and significant wave height shown in tables, which we have used for simulations. Okay, let's get to the actual concept. As already mentioned, the idea is to arrange an outer breakwater ring with an internal floating PV system. The breakwater is comprised of individual trapezoidal modules, as seen from above here. This shape was selected to avoid production of rounded elements and to simplify the manufacturing process. Connections are incorporated between the elements to facilitate continuous force transfer. The selected circular layout shape has the advantage of minimizing force peaks and reducing the corresponding amount of material required. This illustration shows a breakwater module in a slightly transparent manner. The element consists of structured concrete shell on the outside and an inner core, which must be of light material so that the pontoon still floats. In the end, strengthening of the concrete is necessary to realize the force transfer from the connections. Internal walls are also arranged to strengthen the pontoon. What materials are used? The second pillar of the project is the development of new sustainable materials with long-lasting properties. These materials are said to have a low environmental impact, but at the same time high corrosion and biofouling resistance. They are to contain recycled aggregates and replace cement at least partially with granulated blast furnace slag or fly ash. But what is the influence of these new materials on the floating breakwater compared to the usual construction method with normal reinforced concrete as a shell and a very light polystyrene core? I will come to this on the next slides. So this is the typical cross-section of the breakwater. A lightweight core that is protected against external impact by the outer shell. A variety of cross-sections with different widths and draft ratios were simulated using CFD software to obtain this preferred sections which was chosen for its good wave absorbing properties and the fact that it still could be produced and transported using conventional technology. Depending on the size of the diameter of the breakwater ring, the length of a single element is limited to a maximum length of 20 meters. The width is 5 meters and the height is 2.5 with 0.8 meter for the keels. The total weight of one element comes to approximately 124 tons. And initially we used 1.9 tons per cubic meter for the outer shell and 300 kg for the core, which was the target value of the material work package. In further assessment, these values will be adjusted to the actual results of the work package, which do not deviate significantly. The diagram indicates center of gravity and center of buoyancy and the metacentric height. So this graph is only show the proportions. Gray corresponds to the selected cross-section of the project. The red outlines indicates the typical size of a breakwater pontoon that is used, for example, to protect marinas in sheltered areas. And this is just an example of such a breakwater in reality. And these are approximately the dimensions of the new breakwater pontoons. These are not breakwater pontoons, but to get a feeling from the size and the technology which is required, these pictures are quite good. As already mentioned, investigations were carried out to determine the wave breaking and the wave damping behavior. One criterion is the transmission, which describes the proportion of wave energy that passes through the breakwater and acts still on the floating PV system. Various methods were chosen for this assessment and the results are represented here. In the critical range for the floating PV system between 1 and 3 seconds wave period, the maximum transmission was determined with 0.4. This is an excerpt from the CFD simulations. It is evident that the waves behind the breakwater are less pronounced. Should be noted that this example does not consider any stabilizing effect of the ring or the anchoring, which will reduce the horizontal and roll movements. In order for the ring to provide the desired stability effect, it is essential that the load-bearing capacity of the connections between the elements is adequate. The connections are designed in a way that forces and moments are transferred in all directions except the moment around the y axis. Due to the significant cantilever lengths, a hinge solution was implemented here. One component of the connection is a rubber buffer to absorb compression and shear forces. Furthermore, coupling ropes with threaded terminals are used to transfer the tension. The top view shows the mode of action of the connections when absorbing horizontal moments. This results in a pair of forces with compression and tension. And the section shows a load path for splitting forces on tension in the ropes. To be able to estimate the size of the coupling ropes, this diagram shows the breaking loads of different rope types subject to the rope diameter. The bottom line provides the value of coupling ropes used for smaller marina pontoons, and the upper line shows the type of rope that is necessary for offshore conditions. Number of ropes required varies depending on the location. Another component of the system is the anchoring, which is shown here in principle. After evaluating various advantages and disadvantages, the anchoring to chains and driven anchor piles was chosen, also because this type of anchoring can still be used in deep water conditions. In addition, the anchoring should not be too rigid so that the movement of the breakwater is not too restricted and the associated forces are not too great. This diagram shows the movement of a free-floating breakwater in extreme conditions. The point of reference is the center of gravity. As mentioned, the length of the chains and the location of the anchor piles were chosen in a way that the movement of the breakwater is not limited and that there is still a horizontal load application at the anchor pile. In this graph, you can see the displaced system compared to the unloaded system. The same image, just slightly more enlarged. And here's a complete cross-section with 2 anchor points. So even at maximum displacement, there's still a horizontal load application in the anchor pile, and there is still slack in the chain. Accordingly, the movement of the breakwater is not blocked. This is just an example of the location in the Baltic Sea. The chain length and distance to the anchor pile, as well as the number of anchor piles, vary depending on the location. So yeah, that's my last slide. Since the floating solar system does not have a separate anchoring, must be connected to the breakwater ring. However, the PV field should not follow every movement of the breakwater. Therefore, an elastic connection with PP ropes between the components was chosen. This already absorbs a large part of the various displacements through elastic extension. In addition, a transition element was arranged as a load distributor because the connection to the breakwater can be made in smaller numbers but with a larger diameter because a relatively large load transfer is possible. The capacity on the floating PV system is lower, so connection must be used in larger numbers but in smaller diameters. As mentioned already by Balram, SINTEF has tested these joints for load-bearing capacity and durability so that we can assume that they are sufficiently strong enough during the expected lifespan. So that's from my side. Thank you for your attention.
Thank you so much, Thomas. And now that we have presented the core of the project, we would like to invite, if you are finished with your lunch, you to ask us some questions. Now, please just indicate that you want to talk by raising your hand digitally, and or you can write in the chat. That's also okay. So yeah, I see that we already have one from Stanislas. And the question is, was there any cost optimization consideration in design and material choices? And I don't know who we would like to answer that. Is that something for you, Thomas, maybe?
Yeah, maybe. Yeah, I mentioned that already in the presentation that yeah, we considered in the design, let's say, the size of the breakwater pontoons, because yeah, we could also design a bigger pontoon, which would in the end would have better yeah, floating behavior. But in the end, we wanted to avoid using dry docks, for example, to build pontoons. So we wanted to make the pontoons on land with conventional construction methods, and we still wanted to use yeah, conventional technology to lift, to transport, and to launch these pontoons into the water. And therefore, we decided to limit the size and the weight of these pontoons to these dimensions, which were mentioned in the presentation. From the material size, I think, yeah, cost optimization is one thing, but on the other hand, we need to use yeah, recycled material. We wanted to use recycled material because also, especially, for example, cement is limited and has a bad carbon footprint. So using recycled material is good for the environmental. So with this discussion, you cannot always come with cost optimization.
Do you want to comment on that, Stanislas, or should we move on? Okay. I think Thomas Vatin and Satya Shankavasuki has similar questions, which is, what about the estimated gain for waves mismatch losses that you mentioned? And I think I can try to answer that. We don't have an exact focus on that, on wave-induced mismatch losses in this project, but we did do some work on that in Sunlit Sea together with Institute for Energy Technology in another project. And in that project, we did quite exact calculations based on work of, I think, Dørenkemper back in 2019, which had some general model for calculating it. And we did some Python simulations with various frameworks to estimate that based on different wave conditions. So we could input the HS, the significant wave height, and assess the mismatch losses for a given string length. And obviously this thing is heavily dependent on the string length and a number of the number of panels in the string and the effect of each panel. So the numbers that, if I don't recall completely wrong, we were talking about in the operational range of our panels of mismatch losses between 0 and up to 13%. So I think it would be fair to just guesstimate, which this, I have to underline this, okay, a guesstimate. If we start at offshore conditions of around 10% mismatch losses, with these wave breakers, you could probably say that you could reduce it to maybe 2 or 3%, because not all the waves are dampened. So that's, as I underlined, a guesstimate. So I don't know if Thomas or Satya wants to comment on that. Okay. Okay, so then Ninon Maraki has a question. Apart from design and structural details, are there any plans for environmental monitoring in the future? And if yes, are you planning to make your findings publicly available? So maybe Balram wants to have a go at that one.
Or maybe we can ask Heiko, because he's the one who's doing us environmental assessment. Heiko, if you can. Yeah.
Yes, of course. So we are responsible for the overall sustainability assessment, including as a main point also the environmental impacts. And for now, it is planned to have this environmental assessment covering all the life cycle steps during the project. Monitoring would, of course, imply that there is already a big project deployed at the site, and then one would follow up for many years. That's of course not possible within such a technology development project. But I think it would be really interesting to follow up then later, and let's see which possibilities there would be. I don't know if there's any comments on that.
Yeah.
Okay, thanks.
So yeah, it's maybe we give it a half a minute or so to let it sink in. Maybe someone will think of something when the lunch sinks in as well.
Yes, so yeah, this should be mine. Yeah, I think so. Let me check what was the target. Let me go through
So
the
the
numbers.
question,
Yeah,
the
it's to
question
me.
was for regarding reduced LCOE and what was the target there? So
Yeah, let me check the number because we have written the proposal. So it should be, yeah, it was around 45 to 50, something in that range. No, it was 54. That is what we have written in the project. So we will have not done yet the assessment, but that's our target number, 54. 54 euro per megawatt hour.
Pradeep asks, what would be typical wave attenuation achieved / targeted? And who is the best to answer that?
Thomas is the one.
Yeah, I think the objective was to limit especially the waves, the high frequency waves. So with wave periods between 1 and 3 seconds, and I think we have done this with our breakwater quite good. But at a certain point, or a certain wave height, which is always related to a certain wavelength, the whole system just floats with the waves. But in that case, there's no need to break these waves because the whole system just flows with the system.
Rolf Wikborg, you have your hand up, so take the word, please.
Yeah, no, thanks. Thanks for a good presentation. Look, I saw in one of the photos, which is particular interest for me, which Eric knows, there was a wind turbine mounted on the wave breaker. How large forces can you accept on give me some feedback on the potential number of wind turbines, what size, what capacity, what weight that these wave breakers can accept?
I don't think that it wasn't a wind turbine. It was just, I think, an instrument to measure the wind speed. So.
Maybe it was a hope more than.
Regardless, it's interesting to know something maybe about loads we can expect to have on these wave breakers, because it's an interesting thing to place equipment on them. It could be transformer stations, it could be wind, it could be inverters and other things. So, Thomas, do you know anything about the max loads that we can load? What's the additional buoyancy, I guess it's fair to say, and how large structures can we have on these wave breakers? Is that anything that we have assessed?
No, not yet. I think if we want to have some things on top of the breakwaters, we need to assess that separately, or we need maybe separate platforms which are wider, integrated in the whole system.
I'm surprised that you don't have solar panels on the wave breakers.
Okay. I think this is a separate system. Yeah, I mentioned that in the beginning. The other option is to just put solar panels on floating breakwaters or concrete pontoons, for example. But I think in that case, the whole system would be very expensive.
Okay, but it's a good feedback because it's an interesting concept. As we all know, it's good correlation between wind energy production and solar production. So looking at, I'm guessing Rolf is thinking about these miniature wind turbines, vertical, for instance, that could be placed on top of them and
Yes.
combined with the solar. So it's interesting to note, and maybe we should consider in the project at least if we could do some calculations on the loads.
I'm chairman of Nor Hybrid that are producing this wind turbines, and it could be interesting to, as a pilot, mount one on one of your pilots just to test and see.
Yeah. So normally it will act as a floating. You have the floating wind turbines, but in this case it's a vertical wind turbine. So that could be done some assessment. But again, this was not the part of the project. So
no, I understand. Just I don't know. Just a hint. There's a company called Minolite
yes.
that are making the cement float and making it lighter, and that's definitely something you should be in touch with.
Actually, we have been using their proposed solution into designing this lightweight aggregate. So we have used maybe Maria, if you are there in this chat. Akiona, is anyone there? She can comment. Okay, so our project partner, okay, I see. Okay, she's there, but maybe
she's not in, I think.
She's there, yeah. Yes, we can hear you, Maria. So if you can comment on Minolite.
So we use Minolite in both in the lightweight concrete aggregate and in the cellular concrete for the inner core of the breakwater, and it works very well.
Very good. Thank you.
Okay, the chat has been silent while Rolf was talking here, so I don't know if there are any more questions or if we should wrap it up. We're approaching the end of the allotted time anyway. Let's see here, Caris Kutajar. So please go ahead.
Hi, good morning. First of all, thank you for the presentation. Very interesting work. I was wondering, I'm a PhD student at the University of Malta, and I'm also focusing on floating breakwaters. With regards to the transmission coefficient plot, was that generated for 2D or 3D models, please? And I was also wondering whether you looked at wave peak periods higher than 7.5 seconds, because for the Mediterranean and North Seas, you quoted higher periods up to 11 seconds, if I'm not mistaken. So
yeah, so we did the simulations in two-dimensional direction. So that's one thing, and yes, I can try to find my slide. I can show you the combination of peak periods and significant wave heights. Let me share my screen again. Can you see?
Yes.
So we have statistical data for these three locations. And the reason for these three locations was that we have different conditions. So mild conditions in the Baltic Sea with the maximum values of peak period of 6.5 seconds and wave height of significant wave height of 4.4 meters. And as you see, the North Sea, we have peak periods up to 13.6, which is a maximum, and significant wave height, corresponding significant wave height here was 11 meters. So we made simulations with all these values just to see what is the behavior in different wave conditions, and in the end to find out. Come to that diagram. To find out what is the behavior with these peak periods. But let's say in the end, at 7 seconds period, there's no effect of the breakwater at all. So, but even if you make the width double, 10 meters, for example, there wouldn't be an effect because just the pontoon is too light, let's say, compared to the load of the waves. So that's
Yeah. Okay. Thank you for the clarification.
I believe Ali Duman has a question. How about use of pre-stressing to have thin and lighter outer structural concrete? Is it possible?
Yeah, generally yes, but yeah, pre-stress is one thing. Of course, you can apply higher loads in the reinforcement, let's say, but on the other hand, you also need the compressive zone. So just to make it thinner is one thing, but you need certain location where you have these pre-stressed elements, the pre-stressed reinforcement, and we also wanted to have a certain weight of the breakwater. So just to make it lighter wouldn't help maybe to use less materials, but on the other hand, it would affect the floating behavior and the transmission. So we are quite good with the weight that we have now, let's say. And I think, or I believe the production process for pre-stress would be more costly compared to just unstressed reinforcement.
Ali, do you have a comment on that, or does that sound okay to you?
It was fine. He says that.
That's fine. So yeah, please go ahead with more questions if you have them. Rolf?
Yeah, just a comment. I'm pretty sure that within quite soon you'll have carbon-free cement available. So I don't think that's a problem, but it will be probably a somewhat higher price. But on the footprint, I think you should be okay.
Yeah, that's sounds agreeable with what we think in the project. So thanks for that comment.
I think so. The most CO2 simulation will be done by soon. So yeah, since all the materials are available, so that is one of the part of the project to do this integrated sustainability assessment. We will do the cost calculations and the CO2 calculations. So.
Okay, I think respecting everyone's lunch break, I think we should try and wrap up. And yeah, thank you so much for your keen interest and your good questions. And I hope you enjoyed the presentation. We will be assessing internally in the project if we should do another one of these with some of the other focus that we have in the project that we didn't have a chance to talk about this time. So stay tuned on LinkedIn, and we will, if it is another session, we will market it there. So thank you, and bye-bye, everyone.
Thank you. Bye-bye.
Thank you. Thanks.
Bye.
Thank you.